My name is Yong, and I come from the University of Maryland. Today, I'm going to talk about chiral effective theory for lattice QCD. Before my talk, I expect that you have already gone over the lectures on chiral effective theories and understood the basic ideas of chiral symmetry breaking and chiral effective expansion. My talk is divided into four parts. In the first part, I will talk about chiral symmetry in lattice QCD and its breaking. In the second part, I'll show you how to write down the chiral effective Lagrangian for the Wilson fermions, which I call WChiPT for short. In the third part, you will see the results from WChiPT on the meson masses and decay constants. And finally, I will talk about some related topics that is worth us understanding. To begin with, lattice QCD is a well-known non-perturbative approach to solve QCD. In the past 3 decades, it has generated remarkable results on hadron spectroscopy and nucleon form factors, and so on. On the other hand, it has also been a very effective tool to study the physics beyond the standard model. The lattice QCD approach is basically a numerical approach. It works within Feynman's path integral formalism and uses the Monte Carlo methods to calculate the path integrals. This theory is formulated in Euclidean space, and because the calculations are done on computers, the space has to be discretized. Therefore, the space integral becomes summation over all lattice sites, while the momentum integrals becomes summation over all momentum modes in the first Brillouin zone. We should pay special attention to the derivatives in lattice QCD. It is defined to be the difference between adjacent fields, and we have a forward derivative and a backward derivative. So how do we formulate the Lagrangian for lattice QCD? The Lorentz symmetry is already explicitly broken, but we still want to guarantee the gauge invariance. The fermion fields transforms in the fundamental representation just like they are in the continuum theory. But for the lattice derivative, because it is associated with two fermion fields, they cannot transform the same way, and therefore we cannot form gauge invariant bilinear operators that include derivatives. To solve this problem, we have to introduce a gauge link. The gauge link transforms this way, so that when it is approached, when it is attached to the gauge field at x plus a mu hat, it will make it transform just like the gauge field, the fermion field at x. In this way, we can define a covariant derivative for the lattice. We can also define a backward covariant derivative in this fashion. So, with the covariant derivatives, the simplest gauge invariant action we can formulate on lattice is the Wilson action. The Wilson action has a fermion part and a gluon part. The gluon part is also called a plaquette, which I will not discuss here. And for the fermion part, it has a derivative term, a mass term, and especially a Wilson term. The Wilson term is introduced to remove the redundant fermion degrees of freedom, which are called doublers. And also, I will not discuss the origin of the doublers and its problems, but just want you to be noted that here the parameter r is arbitrary and usually it's set to 1. So let's look at the chiral symmetry on the lattice. The chiral transformation is the same as they are in continuum theory, and under this transformation, the derivative term remains invariant, the mass term explicitly breaks the chiral symmetry, so it is responsible for the mass of the light mesons. While for the Wilson term, it also explicitly breaks the chiral symmetry, and in a perturbative calculation, it will generate a critical mass correction to the mass of the fermion. Particularly, this critical mass is of order 1 over A, and it cannot be multiplicatively renormalized. We have to subtract the critical mass from the bare mass of the fermion and then do a multiplicative renormalization of the fermion mass. The finally renormalized fermion mass is the quark mass matrix that we use to construct the chiral effective theory. So with this prerequisite knowledge in hand, we can now study the WChiPT. But before we move on first, I want you to know why we need an effective theory for the lattice QCD. In practical lattice simulations, there are always errors generated by the finite lattice spacing and volume. Therefore, to get the physical result, we have to take the continuum and infinite volume limit. So these limits are taken by taking extrapolations. The chiral effective field theory plays an important role in this extrapolation. First, we get a ChiPT expression for the hadron spectrum and decay constants, and then we fit this expression to the lattice simulation results so that we can fix the parameters in these ChiPT expressions. However, the continuum ChiPT cannot account for the discretization effects, so there are always errors in the extrapolation with continuum ChiPT. To take into account of these discretization effects, we have to design a chiral effective theory for lattice QCD. So let's come back to the lattice QCD. The lattice QCD itself can be considered as an underlying effective theory in the continuum. This is because it has a natural cutoff scale 1 over A. And according to semantic, this effective action can be expanded in powers of A. And we call this the semantic action. The leading order expansion is the QCD Lagrangian. And at order A, the operators the operators that satisfy certain symmetry requirements, including the Lorentz invariance, gauge invariance, parity, and charge conjugation invariance, are all candidates for the effective operators. There are 5 operators that satisfy these requirements. Here, operator 1, which we call O1, is called the Pauli term, and there are 4 other operators. But not all these operators are relevant for the ChiPT analysis. We can use the equations of motion to rewrite O2 and O4 in terms of O1 and O5. Meanwhile, O5 and O3 are proportional to the leading order Lagrangian, so their effects can be absorbed into the renormalization of the mass and the coupling of the theory. In this way, the renormalization equation for the mass and coupling has to be modified by adding the lattice effects, which is characterized by the low energy constants Bm and Bg here. These constants are non-perturbative and they can be fitted with lattice simulations. So finally, the only operator we need to consider at order A is the Pauli term. The Pauli term breaks the chiral symmetry in the same way as the mass term in the leading order effective theory. So they should be treated on an equal footing. In the construction of chiral effective Lagrangian, we should treat the coefficient of the Pauli term ACSW as a non-trivial matrix in the flavor space, just like M. So now we can define our spurions, that is the square of the ghost down masses, as chi and rho. Chi is the same as that in the continuum theory, while rho is due to the lattice effects. The chi and rho will transform in this way to make the symmetry breaking terms symmetric. And the low energy constant B naught is the same as that in the continuum effective theory, while W naught is another low energy constant that should be fitted with the lattice simulations. So how does the chiral effective Lagrangian expand? The scale at which the chiral effective Lagrangian fails is the same for the lattice. That is about 1 GeV, the barrel mass. For WKPT, we should have two expansion parameters. The first is defined as epsilon, which is of the order of p squared over lambda squared, or chi over lambda squared. The other expansion parameter is delta, which is of the order of rho over lambda squared. Let's consider the definition of chi and rho. They are proportional to the fermion mass and lattice spacing A. The low energy constants B naught and W naught, they should only depend on the high energy details that is above the scale of lambda, and therefore, by simple dimensional analysis, B naught should be of order lambda, while W naught should be of order lambda to the third. So we conclude that chi over lambda squared is of the order of m over lambda, while rho over lambda squared is of the order of a times lambda. In this way, the leading order Lagrangian in the WKPT is of the order of epsilon and delta, that is of order m and a, while the next leading order is of the order of epsilon squared and epsilon times delta. Note, we should pay attention that here we do not consider the order delta squared because it is basically of order a squared, but we have only expanded at order a in the semantic action. So we have an implied hierarchy in this effective expansion, that is, epsilon must be much greater than delta, or in other words, m over lambda is much greater than a times lambda. But we should keep in mind that this choice of hierarchy is actually arbitrary. In practice, the relative size of m over lambda and a times lambda is determined by the quark mass and the lattice spacing. So if they are of the same order, we have to consider order delta squared in the next leading order WKPT and should expand to order a squared in the semantic action. But for our discussion here, we just use this hierarchy and drop the order delta squared term. So with this in hand, we can construct our leading order chiral effective Lagrangian. It has exactly the same form as that in the continuum limit, except that the chi in the continuum theory is replaced by chi plus rho. We can expect that the leading order results and its loop corrections will be just chi replaced by chi plus rho. The next leading order chiral effect WKPT can be separated into two parts. The first part is called the chi part, It is of the same form as the continuum theory. The other part is called the row part. It has incorporated the corrections from the discretization effects. In the continuum limit, the row part will be dropped and we reduce to the continuum chiral effective Lagrangian. So here we must pay attention that there are various low energy effective constants, B naught, F naught, L, and W's. They all depend on the high energy scale lambda, as this is the scale that defines the effective theory. On the other hand, they should not be dependent on the fermion mass or ACSW because these are both long-distance physics. However, we should not take for granted that these low energy constants do not depend on lattice spacing A. This is because these low energy constants all depend on the strong coupling G, while the strong coupling G has a dependence on the logarithm of A times the cutoff lambda. Therefore, therefore, the low energy constants still acquire a dependence on A, but it's rather weak because it is at most a logarithmic dependence. So with this chiral effective Lagrangian at order A, we can use it to calculate the meson masses and decay constants. First, the meson masses. The meson mass is divided into the leading order contribution and next leading order loop contribution and next leading order tree contribution. Here the indices A and B are different, and they are the flavor indices and have the same quantum number as psi bar A, gamma 5, psi bar B. The leading order and next leading order loop corrections and the next leading order tree corrections, tree contributions, they both depend on some parameters or constants that need to be determined by lattice, that need to be fitted by lattice simulations. So these are the definitions of these constants. If we compare it to the result from continuum ChiPT, we will find that the leading order mass and next leading order loop correction will just be the continuum ChiPT result with chi replaced by chi plus p, chi plus rho, while in the next leading order tree contribution, it is equivalent to the continuum ChiPT result in the continuum limit, as expected. Then the second application is to calculate the decay constants. The decay constants also have three contributions from the leading order, next leading order loop, and the next leading order tree. And these constants in the results will be fitted according to the lattice simulation data. So up to now, I have shown you how to construct the chiral effective Lagrangian for the Wilson action at order A and use it to calculate the meson, mass, and decay constants. There are still some interesting topics that are related to WChiPT and worth your attention. So let's move on to the last section. The first topic that we should pay attention to is the improved Wilson action. So the purpose of formulating chiral WChiPT is to remove the errors at order A, but this is not the only way. On the other hand, we can improve the lattice action to eliminate the order A errors in it. The strategy is we add some counterterms to the Wilson action so as to eliminate the lattice discretization errors at order A, and then we use the improved action to do lattice simulations. Meanwhile, if we want to calculate the matrix elements of some local operators in lattice QCD, we should also add a suitable lattice counterterm to the local operators and do the simulations. To better understand the improved Wilson action, I can show you two examples. The first example is just the improved Wilson action at order A. So this counterterm is very similar to the order A effective Lagrangian in the semantic action. The only difference is that the gluon field F mu nu is replaced by its lattice version. This is defined to be the average of those 4 smaller plaquettes shown in this graph. And we also have a constant CSW here, which is to be fitted according to the lattice simulations. However, tuning or fitting this constant CSW is very difficult, and people have tried to calculate it in perturbation theory at order G squared. Recently, it has also been argued that this constant can be non-perturbatively fixed with chiral symmetry, which I will not go deeper. The second example is the improved local fields. So here I take the actual vector current as the example. Its counterterm is the lattice derivative of the actual charge. And also we have a low energy constant Ca that can be calculated in perturbation theory, but also are shown to be non-perturbatively fixed in a quenched approximation. Here, quenched approximation, I mean we throw away the contributions of the fermion loops in all the Feynman diagrams. So, with the improved Wilson action, we are forced to go beyond order A in the WKPT. Why? Why do we have to go beyond order A in the WKPT? The first reason is plain. Lattice spacing is not small enough, so to obtain required accuracy, we have to go beyond order A. The second reason is that, as I mentioned, the order A improvement has already become a common practice for lattice calculations these days. So the leading error is order A squared for the lattice simulations. For our WKPT approach to be of practical use, we have to go beyond order A and incorporate the corrections at order A squared. Then, what will happen at order A squared? First, we expect that there will be symmetry breaking terms, and we can use the spurion analysis to render them symmetric and construct our chiral effective Lagrangian. But at order A squared, there will also be symmetry conserving terms. These terms cannot be analyzed with the spurions. To show you what they look like, I provide with you all the effective operators at order A squared in the semantic Lagrangian. So, for example, operator 9 here breaks the chiral symmetry, but operator 11 preserves the chiral symmetry. For these chiral symmetry breaking terms, we can use a spurion analysis to attribute them to the chiral effective expansions. And the difference between the order A WKPT is that for the next leading order, we have to expand to order delta squared. Then the question is, what is the contribution from the symmetry conserving terms? The symmetry conserving terms will only contribute proportionally to the symmetric term in the chiral effective Lagrangian. At the leading order, only the kinematic term is chirally invariant. So the symmetry conserving terms in the at order a squared will only contribute a shift to the constant f naught squared. The shift is is a squared times some low energy constant. So should we include the contributions from this shift? If we take a dimensional analysis, we will find that a squared times the leading order Lagrangian will be of order epsilon a squared and delta a squared, and they are actually of order m squared a squared times a to the third. This is actually much smaller than the next leading order contributions, and therefore we can just neglect their contributions for our order a squared analysis. So in this way, we only need to worry about the symmetry breaking terms at order a squared. With the order a squared chiral effective Lagrangian, we can make our extrapolation for the continuum limit to have an accuracy of order a squared. So to have order be accurate up to order a to the third. So that will significantly improve the continuum limit extrapolation. So finally, the partially quenched theory. With the chiral WKPT in hand, we can use it to extrapolate the results from unquenched lattice simulations with dynamical quarks. So we will have valence quarks, dynamical quarks or C quarks, ghosts and gluons. In principle, the valence quarks, dynamical quark, and the ghosts should have the same mass. But in practice, people set the dynamical quarks to have different mass from the valence quarks so that they can have a larger parameter space. And for the construction of a partially quenched WKPT, we only need to extend the flavor mass matrix to include the C quarks and the ghosts. So the flavor matrix will have two flavors of valence quarks, and the ghosts have the same mass as the valence quarks. And there are three flavors of C quarks which have different mass from the valence quarks. The analysis of the partially quenched WKPT is similar to that of WKPT, and they are actually of more practical use for the lattice theorists. So this is all of my talk. In my talk, I showed that the chiral effective Lagrangian for the Wilson action in lattice QCD is formulated to take into account of the discretization effects at order A. But due to the improvement of the lattice action at order A, we have to expand to order A squared to increase the precision. And so that's all for my talk. Thank you.